Okay, so let us do the refraction of light at planar surfaces. So in this class we'll study the normal shift, okay, due to refraction. Say, suppose an object is there, okay, at a depth of d, okay, and suppose you are observing the object from here, this is your eye, clear. So the light ray is going like this, is the normal, okay, and the light ray is suffering refraction from denser to rarer medium it is going, so yeah, it is refracted away from the normal and it reaches the eye, okay, clear. Now the eye looks back like this, okay, the eye looks back straight, that means to the eye actually the light seems to be coming from this point, right? So this is the image of this object, okay, so it will be perceived that the object is at a lesser depth. Actually the object is at a depth of d, but it will be perceived that the object is at a depth of d dashed, okay, this much, okay, clear, this much is d dashed, clear, okay, fine. So d is the real depth, so d dashed is the apparent depth, okay. So there is a normal shift, that is d minus d dashed, okay. Fine, clear, okay, this much actually d minus d dashed, alright, fine. So we have to calculate this, so in order to calculate, let us write this angle of incidence is I and the angle of refraction is R, okay, fine. So here let us call the denser medium to be mu2, the refractive index, and in the rarer medium the refractive index let us call mu1, okay, fine. So first let's give the name, say M N P Q, alright. So if this angle is I, we know that this angle will also be I, this will also be I, Okay, this is the alternate angle, and if this angle is r, then this angle will also be r, this corresponding angle, right? Okay, so from triangle MNP, what we can write, sine I is equals NP, sine I is NP by MP. Okay, NP by sine I is MP by MN, right? Call it MN. Okay, NP by MN. Okay, sine I. Okay, and so from triangle QNP, what we can write, sine R is NP by QN. Okay, fine. Sine R is NP by QN. Okay. So if I divide these two, sine I by sine R will be NP and NP gone, it will be QN by MN, right? Now see, if the light ray is not very oblique, is not very oblique, that means, observe carefully, this is the light ray. Okay, so if the light ray is not very oblique, that means it is like coming like this. Okay, almost directly above the object. Okay, that means when we observe an object, the eye is not like this, na. We actually observe the object by taking our eye directly above the object, right? So the light rays that will reach the eye will not be so much oblique, right? Okay, they will be almost straight reaching the eye. Okay, so you see this point N is approaching P, so this point N will be very closer to P. Okay, clear? So N can be replaced by P. So we can write sine I by sine R as QP by MP. Okay, so you see QP is D dashed and MP is D, so it will be D dashed by D. Now Snell's law, at point N, what it will give, mu 2, okay, into sine I is equal to mu 1 into sine R. So sine I by sine R, it will be mu 1 by mu 2. So let us put this thing here in this equation. So what you will get, D dashed by D is equal to mu 1 by mu 2. So D dashed will be mu 1 by mu 2 into D. Okay, so we can also write it like this, D by mu 2 by mu 1. Okay, so D dashed is basically D 1 mu 2. Okay, so this will be the apparent depth. Okay, so what will be the normal shift? It is d dash d minus d dashed. So it will be d minus d1 mu 2. So it will be d1 minus 1 by 1 mu 2. Okay, fine. Alright. Here mu 2 is greater than mu 1. That is I at the rarer medium and object at denser medium. Okay, so now if the I in the denser medium and object in the rarer medium, then see what happens. Suppose here is the I, this is E, the I here, this is the denser medium, mu 2, the refractive index, and say here is the object. Okay, so the light ray is coming like this. Okay, suffers refraction at this point and finally comes to I. Okay, like this. Fine, so the angle of incidence here is I and the angle of refraction is R. So the eye will look straight upward. Okay, so see here. Okay, so it seems to the eye that light is coming from this point. Okay, this point. Okay, fine, rather than this point. So there is a shift, a normal shift here in this case. Okay, so what is it? Suppose this height is h, the actual height, and this one is h dashed, the apparent height. Okay, so call it m, n, this is e, this is p, this is q. Okay, so if this angle is I, this is alternate angle I. Okay, and if this angle is R, this is corresponding angle R. Fine, so from triangle MPN, what you can write, sin I is equals Mn by Np. Okay, and from triangle MQN, what you can write, sin r is mn by nq. So if you divide this two, sin I by sin r, mn gone, so you will get nq by np. Now if the light ray is not very oblique, is not very oblique, okay, then obviously if the light ray is not very oblique, then point M and point N will be very close to each other. Okay, fine. If you take the eye exactly below the object, then the light ray will not very much oblique. Okay, it will come almost straight below towards the eye. Okay, clear? Okay, and see, then point N will approach point M, and finally point N and M will coincide. Clear? Okay, we will try to see the object by placing our eye directly below it. Okay, this is common, right? So point N is very near to point M, so N can be replaced by M. So it will be mq by mp. So mq is h dashed, mp is h. So it is h dashed by h. Okay. Now if you apply, suppose this is the denser medium mu2, this is the rarer medium mu1. Now if you apply Snell's law for refraction at point N, what do you get? You get mu2 sin r is equals mu1 sin I. So sin I by sin r is mu2 by mu1. Okay, so you will get, so h dashed by h will be sin I by sin r, that is mu2 by mu1. So h dashed will be h into mu2 by mu1. So it is h into 1 mu2. Okay, so the apparent shift, the normal shift, what we call, will be here h dashed minus h. So it will be h 1 mu2 minus 1. Okay, clear? Here the formula will be like this. Alright, fine. Now let us discuss the critical angle. The critical angle, that is the light ray, we all know this, right? Suppose this is the denser medium, this is the rarer medium. Okay, so the light ray falling on the interface at a certain angle theta c, okay, for which the refracted ray is grazing through the interface. That means the angle of refraction is being 90 degree. Okay, so this angle is known as the critical angle. Okay, the angle of incidence in the rarer medium, in the denser medium, for which the angle of refraction in the rarer medium is 90 degree. So if you apply Snell's law here, you will get mu 2 into sine theta c is mu 1 into sine 90 degrees, right? So sine theta c is clearly mu 1 by mu 2. Okay, sine 90 is 1. So we can also write it like this, 1 by mu 2 by mu 1. So sine theta c is 1 by 1 mu 2, right? Clear? Okay. So from this expression we can deduce two things, as sine theta c is equals to 1 by mu. So as mu is proportional to frequency of light, okay, clear? Okay, then theta c will be inversely proportional to frequency, because theta c is inversely proportional to mu. Okay, and usually mu is inversely proportional to temperature, right? If temperature increases, then mu decreases. Okay, so theta c will be proportional to temperature. Okay, fine. So as temperature increases, the critical angle will also increase. Okay, fine. So these two things they ask you in MCQ or short questions or assertion reasoning question very much. Okay, so now we have a very common question regarding this critical angle, that suppose we have a point source of light. This is a denser medium. We have a point source of light here. Okay, clear? Fine. So they ask you what is the radius of the circular area through which the light ray will come out from the denser medium to the rarer medium. Okay, fine. Let me explain this. Suppose consider this circular area, okay, of radius r at the interface. Okay, now suppose here when the light ray falls on it from the light source, okay, the angle becomes critical angle, okay, theta c. Okay, so the light ray will just graze through interface. Okay, fine. And here also symmetrically the light ray falls from this light source like this at theta c, so it will be the light ray will graze through the interface. Okay, beyond this angle, so every light ray will just make total internal reflection. You all know this thing. Okay, it will fall like this and it will come in the original medium, it will come back in the original medium. Okay, it will go like this, it will come back in the original medium. Okay, so light can only go from the denser medium to the rarer medium, okay, only through this circular area. Okay, only through this circular area light will go, okay, from the denser to the rarer medium. Okay, so they ask you this thing, that what is the radius of the circular area at the interface through which light ray can come out from the denser media to the rarer media from a light source which is placed at a depth of h inside a denser media. Okay, so this thing is h. So if this is theta c, this angle is theta c. So clearly tan theta c from this triangle, we have tan theta c is equals r by h. Okay, now we know sin theta c, if this is mu and this is 1, okay, then sin theta c is clearly 1 by mu, you have seen. So tan theta c will be this perpendicular by hypotenuse, so it will be perpendicular by base. Base will be root over mu square minus 1. Okay, so 1 by root over mu square minus 1 is r by h. So the radius will be h by root over mu square minus 1. Okay, and the area will be pi r square. So it will be pi h square by root over mu square minus 1. Now root is a square, I am doing the square, so root is gone. Okay, fine. Okay, so now the total internal reflection. Okay, here the light ray, while getting refracted from a denser to a rarer media, it falls on the interface at an angle greater than the critical angle. Here I is greater than theta c. Okay, so the light ray actually is reflected back, okay, in the denser media. Okay, so this angle is the angle of incidence and this one is the angle of reflection. So this one is I2. Okay, fine. So here the three words very important. Total. Why it is total? Because 100% energy is getting reflected in this case. Okay, we can prove it from Maxwell's electromagnetic theory. Okay, that 100% energy gets reflected. Okay, in ordinary reflection, some part of the energy gets absorbed. Okay, a fraction is transmitted and the rest of the fraction is reflected. Okay, but here 100% energy is reflected. No transmission, no absorption. Okay, internal, because here the light ray gets back, reflected back in the denser media itself. Okay, so because so it is the reflection phenomena is basically the internal phenomena of the denser medium. It is becoming the internal phenomena of the denser medium, so it is internal. Okay, and it is reflection in the sense that it no longer obeys Snell's law. Okay, it no longer obeys Snell's law, that is the law of refraction. Now it obeys the law of reflection. Okay, the angle of incidence is equal to the angle of reflection. Okay, so in order to make total internal reflection occur, the light ray must move from a denser to rarer medium. Okay, towards, call it towards. And number 2, the angle of incidence must be greater than the critical angle. Okay, fine.